Welcome to This Explainer by Forge College. All right, go ahead and grab your digital hard hats because today you and I are acting as lead engineers. Our main mission? We're taking all your previous coding deliverables and assembling them into a fully operational, testnet deployed, and highly secure Ether vault. Think of this as the ultimate capstone build for our applied Solidity development track. It's where all those theoretical gears we've been machining finally interlock. It is literally so satisfying when this comes together, so let's just jump right in and get building.
So here's our engineering blueprint for today. First up, we'll look at the final capstone build. Then we're assembling contract components, securing the vault, stress testing the whole thing, running some quality assurance, and finally preparing for access control. All right, part one, the final capstone build. Let's see how these pieces actually connect. If you've been following along with the Applied Solidity development track, you already know we haven't just been writing code in a vacuum, right? Building directly on your hard work from last week, where we were documenting the deployment process, our goal today is to finalize the actual contact wiring. We are doing all the heavy lifting right now so that next week, when we get into why access control matters, we've got a rock-solid, impenetrable foundation to build on. Because, you can't exactly put a high-tech biometric scanner on a door made out of cardboard, right? Moving right along to part two, assembling contract components. Time to gather our raw materials. Okay, let's hit the factory floor. To build this capstone increment, we're basically synthesizing three crucial inputs you've already created. Step one is your overarching architecture diagram. That's our blueprint, showing exactly how the ether flows. Step two brings in the state mappings from lesson 2, acting as our internal ledgers to track exactly who owns what. And step 3? That's implementing the payable deposit functions from lesson 3, which serve as the actual intake slots for our vault. We're taking these isolated individual pieces and bolting them tightly together into one cohesive unit. And the absolutely crucial takeaway here is that all these separate files have to consolidate into one single master file, capstonevault.sol. Now, when you're doing this, you've got to maintain a consistent storage layout. In Solidity, the exact order you declare your state variables, like your balances and payment structs, literally dictates where they sit in the contract's memory. If you mix up that order while merging, you create massive structural mismatches. It's basically the equivalent of trying to install your heavy steel vault door on the ceiling. It's just not going to work, and it'll break the whole shebang. Okay, on to part 3, securing the vault. Let's get those mechanical safety latches installed. Look, an open vault is a robbed vault. It's just a fact. So that brings us to our absolute main defense mechanism, the checks, effects, interactions pattern. Honestly, this is a concept you need to mentally tattoo on your brain. Think of it like a strict bouncer at an exclusive club. First, the bouncer checks your ID. That's validating the conditions. Next, they stamp your hand. That is updating the internal state balances. And only after both of those things are totally done do they actually open the door and let you inside, which is the external call. You always verify the user and update your internal ledger before you ever hand any ether out the door. If you hand the cash out first, well, a malicious actor might just run away with it before you ever deduct it from their tab. Alongside that golden pattern, we've got to apply a few more crucial physical-style latches. We use reentrancy guards as a literal deadbolt on withdrawals, which completely blocks anyone trying to recursively drain the vault. Plus, we safely choose to use the call method instead of transfer so we can adapt to dynamic gas limits. We're also leaving a crystal-clear audit trail by omitting events, like deposit, every single time the state updates. And obviously, as professional engineers, we document every single one of these mitigations in line and in a dedicated security.md file. Because as we always say here at Forge College, code without documentation is just a really frustrating puzzle you're leaving for the next developer. Which brings us to part 4, stress testing. Time to push this prototype to its absolute limits. With the vault fully assembled and locked down tight, it's time to aggressively test this thing against real-world scenarios. We don't just hope it works, we prove it works. Notice the beautiful dichotomy here between a normal user flow and a simulated failure mode. Over on the left, we've got account A. They deposit 0.02 ETH, the internal state mapping increases like it should, and they withdraw smoothly. It works perfectly. But then, look on the right. We have a malicious contract attempting a sneaky reentrancy attack, basically trying to call back into the withdraw function over and over before their balance even updates. But bam, our reentrancy guard trips, the transaction safely reverts, and those sneaky robbers completely fail to break our vault's logic. That is exactly what we want to see. To actually verify these outcomes in practice, we rely heavily on integration tests. We run our compile commands using Hardhat or Forge and deploy to a public testnet or a local fork. Then, we meticulously simulate real externally owned accounts, or EOAs, depositing and withdrawing. And we're not just looking for green check marks here. We use provider utilities to capture the actual on-chain balances, strictly verifying that the event logs match the exact way amounts moving through those intake slots. We also double-check that our struct array lengths and mapping values match up perfectly.
All right, Part 5, Quality Assurance. Let's look at our acceptance criteria. Every lead engineer needs a clipboard to stamp the final approval, and this checklist right here ensures your work is totally production ready. For compilation, we verify the bytecode hash is perfectly stable, meaning your code is completely deterministic. For deployment, we absolutely require a valid transaction hash and receipt as evidence. We test our receive and withdraw functions by analyzing exact balance differentials. We ensure state correctness by making sure our view function assertions actually pass. And finally, your security decisions must be properly documented with specific code pointers in your security review. Really, this isn't just busy work. This checklist is literally the difference between a messy prototype and a battle-tested Web3 application. And finally, Part 6, Preparing for Access Control. Let's talk about the final upgrades.
So, with our QA boxes confidently ticked, our machine is technically sound. Let's step back for a second and look at the golden rule of this entire explainer. Treat state invariants as primary. Ensure arithmetic updates to mappings and struct entries are performed before any external calls, so on-chain state cannot be left inconsistent. This is the foundational philosophy behind everything we've just built. You absolutely must lock down your math and your state invariants before you ever interact with the unpredictable outside world. Because if your internal ledger is wrong, honestly, nothing else matters. And because you stuck to that golden rule today, you have successfully built a reproducible, highly secure artifact equipped with clear view helpers. You've officially paved the way for us to cleanly layer in role-based access and ownership models in our upcoming modules. Think about it. We couldn't exactly add an exclusive VIP section until we knew the building's foundation wasn't going to just sink into the ground, right? And you just proved that this foundation is rock solid.
So I'm going to leave you with this somewhat provocative thought to ponder. We've secured the ether flow, sure, but what catastrophic vulnerabilities might still be lurking in your contract if you forget to restrict administrative functions before going live on mainnet? What happens if literally anyone can call a function that's meant only for the contract owner? It would be a disaster, right? Well, don't worry too much because we're going to tackle exactly how to stop that next week. To continue this journey, master access control, and explore tons of other incredible Web3 topics, be sure to visit forge.college. Keep building, keep testing, and I'll see you in the next explainer.